Welcome, it's time for another Heathkit H8 video. So until this point I've been kind of a spectator. I've been building a lot of other people's boards, but I have not designed my own. So in this video I'm going to change that. I'm going to get rid of the CPU board that came in this computer and replace it with a CPU board based on the Zilog Z8000. Now you've probably seen me do some other videos on the Z8000 lately. I've done a video on the Trump card, on the Clover computer, and on the Olivetti M20. The Z8000, I find it interesting. It's quite an old CPU. It's from the 80s. But it was largely unsuccessful in its time, and it was a 16-bit CPU from Zilog. Supported memory segmentation, 16-bit data bus, plenty of address space, a lot of interesting stuff for its time, but it didn't really make it in the market. But I thought I would take this Heathkit computer and turn it into something that ran that CPU. Why not? Let's see what happens.
Okay, let's take a look at some schematics. So the schematic is divided into 4 different pages. The first page has the CPU and the various logic surrounding the CPU, such as the reset, the bus buffers, that sort of thing. Now, if you've looked at my Z8000 modular computer or Z8000 Clover computer or whichever video I had on that, it will explain almost everything on this page. So I'm not going to go into it in very much detail. What we do have is the Z8000 CPU here. It is a multiplexed address and data bus CPU, so these 16 wires have both the addresses and the data. So it has a pair of latches to latch the address bits and a pair of data buffers to buffer the data, and those are turned on and off at various cycles in the CPU. It's also got down here a couple of programmable logic devices where I implemented some logic. So this one here does segment translations. This thing supports up to 127 different segments. Plus, it supports separate instruction, data, and system normal. Don't use those fancy features, but we do use the segments. And then down here, we have another which handles the bus. So it looks at the various states of the CPU, these ST0 through 3 bits, some other lines, and it will generate your memory read, write, IO read, write, strobe, stuff like that, as well as some chip selects for some of the onboard peripherals. Finally, over here, we have the reset circuit. This is the reset circuit borrowed from the Olivetti M20 computer. So what it does is it makes sure that the first 3 words that the CPU reads when it starts up come out of ROM. That will be the initialization vector. After that, it sticks RAM in the lower addresses and goes with the sort of final mapping that the computer will have. Those 3 words that it read at the beginning will end up jumping to the permanent place in ROM, which is in a different segment. You can read up on the Clover computer video or webpage that I got to learn more about that. Okay, here is the RAM and peripheral board. So again, the 16-bit CPU, so everything has to be done in pairs with the memory. So you've got 2 RAM chips, one for the upper data bits down here, one for the lower data bits over here. They're 512 kilobytes each, so it makes 1 megabyte of memory. Similarly, for the flash chips, we've got the lower flash here and the upper flash here. Now you'll notice all of these do not take an A0 address 0 line. They start with A1. That is because A0 would differentiate between the upper and lower halves of the word, and we're doing our transfers 16 bits at a time rather than 8. So we start with A1. Then we have over here, we have the serial ports. I put serial ports on the board using the Zilog SCC chip. Again, the Clover computer video will take you all through this, so we don't need to go into a lot of detail here. Just know that this thing is interfaced to the data bus. It can be interfaced in 8 bits instead of 16. It uses odd numbered ports, so again, we've ignored the A0. And it has 2 serial ports, one of them here, one of them here. It has its own oscillator so that it can be clocked separately from the CPU, because this oscillator will be used to derive the baud rate. Down here, we have a parallel chip. It's actually the 8536 CIO, which is counter, timer, and I/O. At this time, I'm not using the counter timer feature, but I am using the I/O, and I'm using it to implement an interrupt controller. So, total of 7 interrupts come in from the H8 bus, and those will go in here, and they will generate. Where is it? Down in here someplace, right there on this int line. When one of these interrupt bits changes, we will throw an interrupt out here through the non-vectored interrupt. You put that jumper down there. And that is how we will interrupt the CPU. Then the CPU can go in here, take a look, see which device threw the interrupt. This, like the SCC, it's an 8-bit device, and it's hooked up to odd port numbers, hooked up in 8-bit mode. We do have some pull-ups that I put on the ports, so pull-ups on the interrupts, as well as pull-ups on the second port on here. We can use the second port as general I/O port as well as the third port. They're broken out to a cable down here, which we could use to hook up external I/O devices or keyboard or something like that. Page 4 doesn't have a whole lot on it. It just has a MAX 202 serial transceiver. It's hooked up to one of the two ports on that SCC chip, and it comes out to a couple headers. This is the pinout that is used in the H8 computer from its H8-4 serial board. I copied the same pinout so I could use the same cables. Now for the interesting stuff. So up until now, we just described stuff that's part of my regular, ordinary Clover computer, which you can go watch the video on that if you want. But we also have to interface with this with the H8 bus. So let's zoom in here. Let's look at our address and control lines first. Now the H8 bus, it's kind of weird. It is an inverted logic bus. So if you look over here at the connector, which I have right here, these address lines have all got the little bar over the top of them, which means these are inverted. So rather than A0 being active high, it's active low. They did that with all of the address lines. They did that with all of the data lines. But they've also done it with the control line. So where is like I/O write? Now, normally on a CPU, I/O write would be an active low line. They've made it an active high line. So almost everything on the bus, which is these two connectors, is inverted logic. So going back over here and going back up, we use a 74HCT 540 as our bus driver, which will invert the lines going through. So it takes A0 and inverts it. Now, I designed this so that you can turn the bus on and off. So each of these run out to a bus enable pin, which goes out to one of the PLDs on that first schematic I showed, so that when the computer is accessing a local peripheral, like the RAM that is built into the board, or the SCC, or the CIO, the serial or the parallel ports that are built into the board, it can turn this bus off so those signals will not be flying out to the bus. And it does that with all 16 data lines. Whoops. Zoom back in. And it does that with the control lines. So the control lines are going through the very same type of chip that is inverting those lines. So IO read, IO going out to the bus is active high, comes in as active low, goes out as active high. Same bus enabled down here. So when we're not accessing the bus, we will turn this off. It will tri-state all of these lines. And then if we look over here, there is this resistor network here, which will pull those signals down to low so that when the bus is not in use, so when we're accessing local peripheral on the board, tri-state, this pulls it down to 0, ensures that memory reads, memory writes, IO reads do not go out on the bus. Finally, the last thing to describe is the data bus. Now I have to apologize. The only symbol I had in the schematic program was this gigantic symbol that it used here, which is just, it's like huge. It's the same number of pins as this one over, but it's huge. Anyhow, this is a 74640, which is a bidirectional transceiver. Because the data bus is bidirectional, you need to be able to both to put data out on the bus as well as to get data back on the bus. So it is an inverting driver. So as D0 goes through, it comes out as an inverted D0. It's got a couple of lines here. One of them is an enable, and the other is a transmit receive. Now, you can see here we take the lower 7 data bits and we put them out on the bus. And that will make our odd numbered ports work, because the way the Z8000 is designed, it is a big endian computer, and the even addresses go on the upper data bytes. So the even addresses would go on D8 through D15. The odd addresses go out on D0 through D7. So on an odd numbered port, we want the data to go in and out through this 74HCT640. And how do we ensure that happens? Well, we've got a little bit of logic here where we're looking at that A0 line. You recall a few minutes ago I told you we really don't need to pay attention to that line for our memory devices and such, but we do need to pay attention to it on the ports, because the ports we want to treat the odds and the evens separately. So if you get an odd numbered port, walks its way through this logic, gets in here, and enables the odd numbered driver. If you get an even numbered port, it walks its way through here, comes out on this other enable line, will go down here, and it will enable this other driver. And this one takes D8 through D15 and puts it on the bus. Um, so that gets you both the even and the odd ports working.
Okay, here is the completed Z8000 CPU board. Here, let me pull this little piece loose so that we can see down here is the Zilog Z8000 CPU. Up here we have a couple of RAM chips giving us our 1 megabyte of RAM. We have some flash memory chips giving us our 1 megabyte of ROM. We've got the bus and memory programmable logic devices. We've got various transceivers over here that hook up to the H8 bus. We have this little piggyback board, which I had to design because my original implementation was faulty. So when I originally designed this, I designed it only to work on odd numbered ports. That's fine. Using my own Clover computer boards, I can decide to put everything on odd numbered ports, but Heathkit, when they design their computer, uses both even and odd ports. So over here we have the parallel port chip, the CIO, and then we have the serial chip, the SCC. We've got a couple connectors over here that match the H8 pinout for the serial connectors. Your RS-232 transceiver, little regulator here to give us 5 volt on the board, and the connectors going to the H8 backplane. Now this is actually a complete standalone single board computer, so it actually has a power jack here if I wanted to, and during development I did do this. I could just plug in 5 volts here, plug in a serial there, and you've got a workable computer. But the idea with the Heathkit H8 project is, this bus will be attached, and we can send, I/O requests out through this bus and use some of the H8 peripherals, which we will go ahead and do in this video. Okay, it's time to add the Z8000 CPU board to my H8 computer. Let me go ahead and plug it in here. Normally you'd put a CPU board way up here in the first socket, but it's been a little bit easier to work with this further back socket on the back plane. You also have to plug in this little pigtail cable here that hooks up to the front panel, which handles the front panel's interrupts. Okay, let's turn on the computer. So it comes up and the panel monitor loads just like any ordinary H8 computer. We can go forward through memory. We're currently looking at address 000004, and it has a value of 250 octal. Now we could change that if we wanted to, so I'll hit Alter. 1, 2, 3 automatically goes to the next address. So if I go out of alter mode, go back, there's 123. I'm just blowing away random addresses in memory while the computer's running. It's not hurting anything. So the Z8000, it is a segmented CPU, supports memory segments up to 127 of them of 64 kilobytes each. It's a 16-bit display, can only display a 16-bit address. We need like 127 bits, so I added an additional register, not a real CPU register, kind of a fake one called the segment register. It's as close as you can get to a G over there in a 7-segment display. Anyhow, the segment register is currently set to segment 1. We can change it, alter 0000003. Now we're looking at segment 3, which happens to be where the CPM kernel is running. You go back to memory, the address mode. We can see that the byte here has changed because we're looking at a different segment now. This is address 4, segment 3. Now I can display something more interesting. Let's go out to 174.351. 174.351. So in the CPM kernel, I implemented a counter that is hooked up to the interrupt that is refreshing the displays. Every time it does a refresh, it increments this counter. This is at memory address 174.351 octal. So if we go up, this is the least significant bit. It's changing very often. Go up and look at another more significant byte. We can see it changes less often. It's actually 32 bits, so we can keep on going. Now, so far I've showed you this operating in octal mode, which is kind of how the original H8 worked. It's kind of an iconic thing that this thing was octal, but in later versions, Heathkit added a way to use hexadecimal, so I added that as well to my monitor. So if we go in here, we push the radix button, now it is in hex. Much easier to use. The keypad actually has hex digits on it so that we can pick a hex address if we want. Okay, you might say, well, that's great. I love the front panel, but what's it like as a real computer? What's it like to go in through the serial console and do something on it? Well, let me go ahead and set up the laptop, get in on the serial, and we will reboot. There we go, and you see CPM has booted. Now the front panel monitor, you know, it continues to run while CPM is running. So over here in CPM, you know, we can run something like the maze program. You know, we've done all this before. There's maze. It's a little bit too wide for my terminal. We can load Zork. Again, we've done all that before. You know, it's your standard CPM 1.1 computer. You've seen me do this with the Clover computer video. I've got a bunch of stuff loaded. It's loaded onto the flash ROM that's in there. But let's try to do something where we use the front panel monitor and the CPM together. So I'm going to load DDT. That is the sort of the debugger that comes with CPM. Right now it's looking at address 01. So it starts with the segment number. So 01000000. It's got an E8 OD there. Here, let me switch this to hex mode. So there you can see the E8. Now let me S01000000. And let's change it to a, I don't know, a 12. Boom, there we go, look at that. It changed it to a 12 on our monitor. So let me exit that. And you know, here, let me D01000000. There's our 12 in memory. And now if we go in here and we wanted to alter something from the front panel, let's hit Alter O A B. Why not? Now if we go in here, 0100. Yep, it changed to an AB. Exit alter mode. Anyhow, so that is kind of showing how this could be useful as a diagnostic tool. You know, you can, while programs are running on the computer, you can go in there in the front panel and you can actually watch what's going on in memory. If you knew an important address, you could watch it. You can change memory. You know, you could actually, if you knew the right addresses in Zork, you could probably hack Zork while it's running. Anyhow, this is not really supposed to be a CPM video, so let me go ahead and finish this up. Okay, I hope you enjoyed this video. I had a lot of fun making this project, this new CPU board. Right now it only really runs the panel monitor as well as CPM 8000. But, you know, over time I will see if I get some cycles available to work on the software. Maybe I can make it work with the some of the Heathkit peripherals like the H17 floppy drive or the H37 floppy. We'll see where we get with it. Thank you. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.